explorer. Searching for the origins of our universe. And charting a safer path to other worlds. I am a helper, moving us forward one step at a time, and giving voice to every emotion.
I love you.
I am a healer, modeling the future of medicine. And finding a needle in a haystack when every second counts. I am a visionary, uncovering masterpieces lost to the ages. And finding new adventures in a galaxy far, far away. I am a builder, driving perfection in everything we create. I am even the narrator of the story you are watching. And the composer of the music. And when the world faces its greatest challenge, I give us the power to take it on together. I am AI.
So with this video, I believe you guys are all settled down. So let's get started with today's talk, right? So today we will be talking about NVIDIA's A100, and we'll be taking a stroll down the line to find out all the new features that are available inside this miraculous GPU, right? I am Dr. Pallab Maji. I am a Senior Solutions Architect, Deep Learning here at NVIDIA, stationed at Bangalore, and I take care of global system integrators and cloud service providers, and I work with them very closely in adoption of our GPUs. I evangelize and I work with them in getting the customers onboarded onto the GPU platform. And today I'll be talking about NVIDIA's newest addition to the family of GPUs, that is based on the Ampere architecture and named as NVIDIA A100 GPU, right? So today's agenda is that we'll start with a short introduction to the accelerated computing. Then we will see what this A100 GPU, the newest member of our family, is all about. We'll talk a little bit about Ampere architectures, and we will go into the detailed benchmarkings that we have done across different type of workloads, both on the artificial intelligence as well as on high performance computing. And then we'll have some time left for a Q&A session, right? So as Deepu have already mentioned, please do post your questions onto the chat window, and I will take them towards the end of this webinar. So starting with, so we have been in the field of accelerated computing for more than 25 years now. And we have been doing this for a long time. We used to be accelerating graphics initially, with our GPUs, but then soon we realized that graphics processing units, or GPUs as we know them, are excellent candidates to accelerate parallel workloads. And since artificial intelligence and many of the high performance computing components are extremely parallel in their nature, GPUs form an inherent choice of hardware to solve this kind of algorithms in the in a way where you have very low latency and very high throughput, right? The newest member, as you can see in this particular field, is the DPU. DPU stands for Data Processing Unit. It's the new class of programmable processor that combines three key elements, right? It basically consists of programmable multi-core architectures, which is tightly coupled with a lot of SoC components, and has high performance network interface capability to pass in the data onto the GPU, so that the GPU does not get strangled for data, right? So GPUs are extremely fast. New age generation of GPUs are performing really fast, and that we will see in couple of slides later as well. But to keep up with the speed of the GPUs, we need to pass it on with very high, with a very low latency of data. And this data processing unit primarily helps us doing that. CPU and GPUs are the known components of this structure, but nowadays with the smart NICs and these DPU processing units are the key component which actually helps us achieve this high-end data center scale of computational workloads. On top of these hardware, we have our full stack software, which is developed on top of CUDA architecture. And this CUDA architecture is one architecture which spans from different different GPUs across our portfolio. Right. So to achieve all these things together, we have a very high speed up. We have a full stack software built on top of CUDA, and we have the data center scale devices. And we coupled with one architecture, we have been formulating this accelerated computing workloads, and we have been serving our customers with the kind of processing power that they need to process today's workload in the field of AI and ML and HPC domains. Right? So as we can see, the challenges in our regular workloads that we see when we work in the field of artificial intelligence and machine learning, and if we track them over last 1 decade, we can see that there has been an exponential increase in the demand of computation. On the left-hand side, you can see early last decade when AlexNet was developed, and that which created this artificial intelligence boom. And right after that, you can see there has been development of numerous different types of architectures which are today surpassing the human baseline of accuracies, both in terms of both in the field of computer vision as well as in the field of natural language processing. And there has been more than 3,000 times increment in the kind of computational demand that we see during this time period. Along with that, what we are seeing is that millions and millions of devices are being equipped with artificial intelligence. There is everyone today who is alive is in some form being touched by the field of artificial intelligence. It is 90% of us in our day-to-day life use artificial intelligence, be it while we are using our smartphones, or be it when we are going out for shopping for different things, or be it in our medical domain. Right. So with respect to these kind of workloads and the kind of computational need, what has been in what has been the demand. Artificial intelligence and machine learning requires a huge amount of computational resource, no doubt in that, but we need to provide them at different scale as well. So there are different forms in which artificial intelligence exists, be it traditional machine learning or data analytics or deep learning, and those intermediate steps in which we develop these kind of algorithms, be it training, validation, and inference or deployment. We have seen different type of computational load that is required. So today's hyper-converged data center looks something like this, where we have the demand of this computational power at different instance of our development in a different way, right? So we need an elastic data center. The problem is that we are so there are different kinds of GPUs or hardware accelerators that are available for training, that are available separately for data analytics workloads, and for inference workloads. These hardware devices are different. So to add, so the main problem right now that we see in a data center is that we need different kinds of hardware to target different workloads of artificial intelligence and machine learning, and at their different juncture of development as well. So we started reimagining these kind of situations some time back, and we started working towards it. And we came up with few breakthroughs which we believe can actually fuel the next era of these accelerated data centers. And today we see that data center is the scale, is the unit of computation for AI and ML applications. We are based on the kind of data sets that we are working with, the amount of data that is available, and the kind of models that we are working with. Those models are huge. Just around 3 to 4 months back, there was a model which is currently the state-of-art model in the field of natural language processing, and that model is called as GPT-3, and it takes around 175 billion parameters. You can imagine that the previous state-of-art model was taking roughly around 8 billion parameters. So you can imagine the uh, uh, kind of growth in terms of computational complexity, the demand in terms of computational complexity that we require. And these models needs to be deployed, and they need to be worked upon in certain way that we can actually use them in real time as well. So with this kind of demand and complexity, what we have figured out is that we need a huge improvement in terms of performance. At the same point of time, we need to be elastic in our scalability as well. And we have come out with newer architecture, with this new architecture, which can help us solve these problems. So just a couple of months back, we actually launched our newest architecture, Ampere-based GPU called as A100. This A100 GPU is available in two form factors. One is SXM form factor, and the other one is PCIe form factor. And the kind of performance that we see over our last generation is quite huge. We are getting around 20x improvement over FP32 training in deep learning workloads. And on in-date inference, we are again getting around 20x of improvement over our previous generation Volta architecture. On HPC workloads as well, and as we all know, majority of the high performance computing workloads are carried on in FP64. And there we get a huge performance of 19.5 peak teraflops, and that is around 2.5x improvement over Volta architecture. One of the newest addition to this new architecture is called as multi-instance GPUs, which actually allows us to take one GPU and break it into 7 smaller GPUs. So this kind of improvement, as we see over our previous generation, both in terms of performance as well as in terms of elasticity, where we can actually break up bigger GPU into smaller instances of GPUs, actually is one of the major key factor which helps us in making this device a device which is data center scale and elastic at the same point of time, which can take care of multiple different workloads in its different configurations. So So moving forward, what are these internals that makes these kind of performance improvement and this kind of elasticity in our A100 GPUs? So first and foremost, of course, we have the world's largest chip on 7 nanometer with an HBM2 memory, the GPU memory. So this particular chip is providing us 54 billion XTORs of performance, and along with that we get our third generation tensor cores. This third generation tensor cores are 20x times better in performance compared to on TF32. We will come across what this TF32 is, and is way faster and flexible compared to our previous generation of tensor cores. Along with that, we have also introduced the a new sparsity, so spatial sparsity acceleration module, which actually gives us a huge performance boost, because as we know, majority of our deep learning models, as deeper we go in the layers, the feature vectors becomes that sparse, and this sparsity is it kills the performance heavily if we do not handle them properly. So currently, with this newer addition of sparsity acceleration, we can actually gain a huge performance boost in our Ampere architecture. The third and the most important, as I said, is the multi-instance GPU. We will be talking about this extensively in our coming slides, where we will see how we can actually take the entire GPU and break it into smaller GPUs as and when required, so that we have an elastic GPU which we can mold and shape based on the requirement. We need not to spend the entire GPU in doing a smaller workload. The final part of these 5 pillars that we see over here, which makes this A100 GPU as great as it is the introduction of the third generation NVLink and NVSwitch. With this, we have now interconnect between these GPUs, which is twice that of our previous generation. So in previous generation, we had a 300 gigabyte Gbps data transfer in between GPUs, whereas now we have 600 Gbps of bidirectional data movement bandwidth. So let's double click on each of these points and try to go a little bit deeper. And we start with the third generation tensor cores. So as we all know, there are basically two or three standard formats that of representing a particular number that is available, right? We have IEEE FP32, which has 8 bits of range and 23 bits of precision with 1 bit as a sign bit. And then we have FP16, which has 1 sign bit, 5 bits of range and 10 bits of precision. And we have int8, right? So these are commonly known. What we understood from our literature survey and from our experience and our experimentations is that for deep learning applications and machine learning applications across different domains, the precision is not that not that important to keep for the training during the training time, but it is very important to have a very high dynamic range. And for that, we actually introduced two new representation of two new number representation, as you can see over here, called as TF float and B float 16. TF float 32 is basically a representation in which a number is represented by one sign bit. We take the best of both worlds from FP16 and FP32 and club them together to make this TF32. So as we discussed, with this with FP32 we get a very high range, but at the same point of time we spend lot of bits in the precisions, and because of that the movement of memory is costlier compared to FP16. So the training time is of course higher, but at the same point of time we get a higher at the same point of time with FP16 we do not get enough range of the numbers, right? So that's why what we did is we took 8-bit range from FP32 and the precision from FP16 and clubbed them together to make this TF32. And our newer generation of tensor cores are equipped to work with TF32 representation of numbers. With this, what we have of course designed the tensor cores with to not only accommodate FP32, FP16, and TF32, but also with the float 16 as well. And at the same point of time, we have this hardware acceleration of tensor cores, which accelerates fused multiplication and accumulation operations. Right. So that is of course improved, but at the same point of time, we have brought in these newer formats to increase in the performance way past that we have seen from generation over generation earlier. So that's primarily how a tensor core is designed and how they operate. Moving on to the next part, which is multi-instance GPU. So multi-instance GPU, or in short, as we like to call it as MIG, is basically the component which gives the elasticity of this GPUs. So imagine if you have a DGX A100. A DGX A100 comes with 8 GPUs, 8 A100 GPUs. These 8 GPUs can be subsequently broken down into 56 smaller GPUs, each with 5 GB of GPU memory. And we can distribute this to 56 different people to do their workloads. At the same point of time, we can, in fact, that is how MIG operates. So it will help you in segregating it into one GPU into 7 independent GPU modules. But at the same point of time, we can take this entire system, and with NVLink and NVSwitch, we can actually link multiple of these systems together, and we can train one big model in multiple of the system as well. So that's the kind of elasticity we are talking about when we talk about A100 GPUs. So we can go down on the down as low as a small GPU, and we can club all this together and can make a huge DGX pod architecture, which with which we can actually hit. So if you are aware, we have developed an in-house cluster called as Selene, which is number 7 in the top 500 supercomputing clusters. So that's the kind of agility we are talking about. That's the kind of scale that we are talking about over here. Now, what is the advantage of MIG? The advantage of MIG is that earlier with our QVDA, with our grid computing software, you could, of course, split a V100 GPU into multiple VMs. But the difference is that in those cases, your memory was only isolated, but the compute element used to be time shared between multiple people. But here in this architecture, what we have done is that we have dedicatedly segregated or isolated these individual instances, and we have made them in a way that not only the memory but also the L2 cache, the underlying SN which crunches the number, the bandwidth, and this isolation provides a complete GPU on its own to maintain the quality of service. Right. That means you are not going to share your compute with anybody else. The amount of compute that you require is guaranteed to have with you at all time. That's the benefit of MIG or MIG. Along with that, what you can do is you can not only divide it into 7, have multiple different ways of splitting these instances. You can have a 3 and 4, a combination of 2, 2 and 3. In that way, we can choose the kind of combination that you want to have based on the workload. At the same point of time, because of this isolation, you also are guaranteed to work with different workloads. As you can see in this particular instance, there is an inference that is happening over here using our TensorRT engine. There are a few TensorFlow based codes that are running over here, probably some small training jobs or so. And there are 3 individual people working on Jupyter to develop some kind of code. And then there is the last instance where somebody is using it for an HPC application. So you can have multiple different people working on the same GPU, and each of them are guaranteed to have the equal amount of compute. Apart from this, it also MIG is also supported on top of Docker, Kubernetes, and virtual environments. So you can do it on bare metal, but you can also choose to work on Docker and Kubernetes and virtual environments as well. The third and one of the most important aspect in field of deep learning that we see is the structural sparsity, how we have been able to tackle it. So structural sparsity, as I mentioned earlier, most of our, as deep we go into the neural networks, the matrices become sparse and sparse. And by sparse matrix, what we mean is that majority of the values are 0. Okay, that means there is no need of computation, but nonetheless, we still go ahead and do it, right? And if we go ahead and do, if we have a mechanism, if we have a mechanism where we need not to do those computations, if we have a 50% sparse matrix, then we can actually do 50% of the compute rather than doing the 100%. So these kind of structural sparsity modules are extremely important in understanding those sparse metrics, and then doing this doing this computation in the sparse matrix environment, and getting those benefits of not computing those those 0 elements, or computing only those non-zero weights and activations. Right? So that's the benefit of this new structural sparsity, which we have, which in many of the cases we have seen around 2x faster execution that we can see over running it on running it without structural sparsity mode on. Here we can see that there is an example where we have trained BERT large, right, with and without sparsity. And here we can see the inference results where with a batch size of 256, and we can see that the kind of performance improvement, which is 1.5x. Overall, as we said, this entire unifying all these different type of advancements that are available in our newer A100 architecture, we get a huge speed up in performance. Now I will try to showcase you some of these some of the different types of workloads and how we have been benefiting over our previous generation and what kind of performance you can expect when you start working with A100 GPU. So say for example, you are working with a V100 GPU and you are trying to train a BERT large model. The amount of training time that you are investing currently is almost 6x higher than if you would do the same training on TF32 with a A100 GPU. Now it's not that it is here. What I am trying to uh, say is that it's not about just getting the workload process as fast as possible. It's not just that. With this, any engineer or data scientist or researcher, what ability he or she gets is that they can train their systems for multiple different hyperparameters. They can spend lot of time in actually curating, in actually formulating, uh, in actually finding out that how to make a use case or how to make a model which is better in terms of accuracy, in terms of throughput, and so on. So you as a data scientist, you as an engineer, you as a researcher, you can actually devote more time in hyperparameter tuning, in doing experimentations with different types of architecture, in doing experimentation, and in figuring it out that how you can add different components to your loss function, how you can add different diversity to your data sets, how you can add different types of augmentation concepts to your data sets. It gives you that flexibility, it gives you that time where you can actually try to address different aspects of developing your model rather than waiting for the model to get trained and then get the results and then try to bring in your insights and then go ahead and do it. So whatever you are doing right now, these kind of benefits gives you the ability to right. We have, and as we know, these systems do require, so that is the DPU part. We talked about the GPU part, and in the CPU part, we have dual 64 core AMD ROM CPUs and with 1 TB of RAM. To power these devices, we have also 15 TB of internal Gen 4 NVMe SSDs, which are available. So these are Gen 4 SSDs, NVMe SSDs that are available inside this box. So that's primarily the kind of compute system that is available inside compute performance that is available inside this DGX A100 box. And this, as we can see, is a universal AI system, which irrespective of your workload, whether you are doing data analytics or you are training big or small models in machine learning or in deep learning, or whether you are doing inferencing, you can actually use this kind of machines, and you can tweak them, you can size them accordingly using the MIG mode, and you can provide you can develop in smaller systems which are dedicated for inference. At the same point of time, you can have other graphics cards where you can run training of where you can run multi-GPU training of models as well. So moving forward, looking at, earlier I talked about BERT as an example, right? Now, BERT is basically a single sole example of one use case in NLP. Then you must be thinking around that, how is the performance in other domains? So here what I have done is I have tried to club in different types of benchmarking that we have seen in different types of workload. So here, as you can see, we see lot of improvements in NLP based systems like transformers, GNMT, BERT, and so on. At the same point of time, we have text to speech conversion systems, we have recommender systems, we have tested it across speech recognition systems, and of course, computer vision tasks as well, like Mask RCN, Resonance 50, and so on. And and across different domains, we have seen significant improvement in performance. The same with HPC as well. In HPC as well, we try to look into different. We showed you earlier Berkeley GW benchmarks, but here you can see there is NAMD benchmark, the GROMAX, Amber, LAMPS, RTM, Berkeley of course, and then Chroma as well. So these different types of benchmarks across different type of applications, we can see significant boost in performance. Last but not least, we need to talk about data analytics as well, right? So TPCX BB stands for big data benchmarking, actually. So this TPCX does a lot of other type of benchmarking. BB is the specific benchmarking which is done for big data analytics, and there we have been we have submitted our results, and we have seen that we are using DGX A100 and with Rapids, we are actually 19.5x faster than the previous best. So these kind of improvement we have seen on big data analytics benchmarking as well. So we have there is a big blog around it that was that created huge uh, interest in the community. You can find it out in Google as well. And there you can see that using these systems and using DGX A100 and with Rapids is our data analytics stack, software stack. And using this Rapids, we were able to crush our competition and we were actually 19.5x better or faster in those benchmarking as well. Now, what that exactly means is that same benchmarking, if you see those benchmarking results, you will see that roughly around 350 CPU servers, which takes around 300 kilowatts of power, is actually gained by 16 NVIDIA DGX A100s, which takes roughly around 100 kilowatt of power. That is the power difference. You can imagine the cost difference now. This is an equivalent performant systems, right? So on the left hand side, these CPU clusters take around 22 racks, that much of space in your data center. This takes around $23 million to put this kind of a system together. Whereas on the right hand side, you see that we can generate the same kind of performance with a much cheaper, much less power hungry, and with a much better space conserving system, which is 1/7 of the cost and 1/3 of the power. And just using 16 DGX A100, we can beat we can be as good, or we can actually better the results from a 350 CPU servers. So that's the kind of performance, or that's the kind of cost saving we are talking about over here. Now we have talked about the hardware part, right? I want to specifically now talk about some of one of our software hub where we have kept all our optimized software, which is free for anybody to use. Uh, so when you work with NVIDIA GPUs, right, I would like to introduce you with NGC. So what is NGC? NGC is the hub that actually hosts software optimized for NVIDIA GPUs. It basically houses all the softwares for deep learning, machine learning, and high performance computing. Right. So NGC basically contains different softwares in containerized format, which are optimized to run on any kind of NVIDIA GPUs. And this accelerates the productivity and the ease to deploy, where the users are basically mostly can focus on developing and deploying their solutions rather than fidgeting around. Right. So with NGC, what you basically get along with this as is lots of pre-trained models as well. So these pre-trained models have been trained internally on our clusters for thousands and thousands of hours. And most importantly, you can get pre-trained models which have been trained on domain-specific data. Now, what do I mean by domain-specific data is that these pre-trained models have been trained on data, which is, say, for example, if you are developing an application on healthcare domain, right? So if you take pre-trained models which are available in NGC, which are of healthcare domain, then you actually these pre-trained models have been trained for thousands and thousands of hours on healthcare data, and then you can bring in lot of then when you bring in these pre-trained models and try to fine-tune your application, it is way better than using a pre-trained model which has been trained on generic data, right? So along with this scripts and containers, we also with this pre-trained models and containers, we also have model scripts with which you can start training your own models as well, right? And these optimized models these scripts are available for different type of GPUs and where they are there, right? So if you want to work on,
Hello.
yes.
Philip, sorry to interrupt you. Actually, we are running out of time. So I'd request you to, make it more faster.
Yeah, so we will be done in couple of minutes.
Yeah, yeah, please.
Yeah. So so be it your on-premise cluster or be it your cloud, we would be able to help you download your containers and start working with it. In E2E as well, the devices that are available in E2E, all the GPU devices, you can easily work with NGC software hub. You can pull the containers and you can start working with it. Finally, as I have described, you have different types of workloads, be it data analytics, artificial intelligence, or high performance computing. We have the software solutions to target all these domain as well. I would also like to draw your attention to the fact that we are running a DGX A100 test drive program. So it is as easy as 1, 2, 3. You can connect to Hubert or Deepu to know more about them. You basically need to get an access to a DGX A100. You just share your use case and application and the kind of expectation that you are having to gain from this experimentation. And we can provide you with a DGX A100 access for a couple of days where you can try to train your system and get advantage of seeing the powerhouse in action. Going forward, I would also like to take a minute to talk to you about our GTC conference. So our GTC conference is going to start from October 5th and going to go for 5 days till October 9th. You can register in the given link, and if you are from some, if you work for an enterprise company, then you can reach out to Deepu or Hubert, or even to me, and we can get you some discounts, or we can get you some free passes as well for that. So with that, I closed my session. If there is any question, I would like to take them.
Yeah, Pallab, there is one question.
Yes, please.
Yeah, from Karan Khabra. What is the difference between A100 and RTX 8000? So they are a deep learning startup, and they're into computer vision for media and entertainment. So they're trying to optimize face, emotion, object, and action detection models. So they're unable to improve over 33 frames per second of processing.
Okay, so of course there are many structural differences between A100 and RTX 8000. RTX 8000 is primarily meant for professional graphics and visualization workloads. They do not have enough computational components, like in terms of CUDA cores or in terms of tensor cores, as compared to A100. Of course, again, you have to also understand that RTX 8000 is based on previous generation Turing architecture. So there are a lot of advantages that you can get out of using A100 over RTX 8000.
Sure. I hope it answered Karan's question. So other questions we'll be taking it offline. So we'll be getting back to you. So I'll be winding up it now. Thank you, Pallav, for the very interactive session. It was very valuable. I hope all the attendees got a good knowledge overview about A100. And thanks a lot.
Thank you so much.
Yeah, great. Thank you, everyone. We appreciate you being here. We'll be conducting series of webinars on AI every month, fourth week. So thanks again for joining us today, and we'll see you back again. Thank you.
Thank you so much.
Yeah, thank you, Pallav. Yeah.